Good afternoon to all the participants. Hello. I think participants are already joined. Good afternoon to all the participants. Today we have last day and the keynote speaker we have joined Dr. Ram Prasad Padhy from IIT Bhubaneswar. Earlier he was worked in IIT Kanchipuram and now he moved to IIT Bhubaneswar. Before going to start his session, I'm going to give brief introduction about Dr. Ram Prasad Padhe. Dr. Ram Prasad Padhe is currently serving as an assistant professor in the Department of Computer Science and Engineering in School of Electrical and Computer Sciences at Indian Institute of Technology, Bhubaneswar. He received his BTech and PhD degree from the National Institute of Technology, Roorkela, and prior to joining IIIT Bhubaneswar, he was an assistant professor for 3.5 years in the Department of Computer Science Engineering at Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram. He has 5 years of cumulative industrial research experience with Samsung Research Institute, Delhi, and Siemens Technology and Services Private Limited, Bangalore. His research interests include machine learning, computer vision, autonomous robotics, and visual surveillance. His research publications comprise international journals, conferences, and patents in these domains. He had also served as a reviewer in many peer-reviewed international journals and conferences. Now I am requesting to Ram Prasad Pade to start your session. Thank you, sir.
Thank you, sir, for the introduction. Let me share my screen
Yeah, yeah,
and let
please
me know
share, sir.
once my screen is visible.
Yeah, yeah, yeah. Please. Yes, sir. Your screen is visible. You have shared. Please share your PPT.
Okay. Is my PPT visible?
No, no. Now it is visible. Please make it full screen mode, sir. I think it is.
Yes.
Uh,
Let me go to the first page.
yeah,
Okay. Yeah.
yeah, yeah, yeah. You can start, sir.
Just okay. Okay. Yeah. So good afternoon, everyone. So for today's talk, my topic is how we can leverage artificial intelligence and computer vision for autonomous vehicles. So in this, you can see there are three very state-of-the-art techniques that we are using. First thing first is this artificial intelligence, and it is not something new to us. In many fields, whether it is computer science or even electrical or electronics, or even you go to any field like mechanical or civil, you will see that artificial intelligence is being used nowadays, right? Everywhere. Even you go to the government of India, different schemes are coming. You will see that some in some way or the other they are encouraging us to use this artificial intelligence. So it is not something that new. It is like already it has got so much of traction and people are using it. So one of the techniques is artificial intelligence. Then this computer vision. So computer vision in general is like how we can leverage different vision sensors to find out or to extract information from the data, right? So it could be in general we have a understanding that vision means only based on videos. Okay, so in this video lecture we are going to say it's not about just videos or the camera data, rather it could be from any sensors. Like in this talk generally we will focus on how lidar sensors can be used for autonomous vehicles, right? So then the third term is these autonomous vehicles, or in layman most people would know like self-driving cars. So nowadays you will get so many articles where you see that autonomous vehicles are being run in this kind of areas, or self-driving cars are running successfully. This kind of articles you would be finding. So in this talk we will generally focus on how this artificial intelligence and computer vision in general can be used for these autonomous vehicles, and what are the different techniques that are needed for this. So in this, we will focus on some introduction about the self-driving cars or the autonomous vehicles. Then we will see how this AI or machine learning revolution has happened. And whenever we use this term AI and ML, is it the same or is it different? And how also this deep learning revolution has happened after that, right? Then we will see how this AI ML technique in general can be used for the self-driving car technology. We'll focus on different kinds of sensors that are being used for self-driving cars, like this camera sensor, very general sensor that is being used by many different fields. So we'll focus on the camera sensors. Then we will also focus on the other sensor called as light detection and ranging, which is the lidar sensor. Mostly in robotic system, you will see that lidar sensors are being used for getting the 3D information. Then we will also focus on how radar sensors can be used in autonomous vehicles domain, and also we will see how this GPS, which is global positioning system, and there is a sensor called as IMU, inertial measurement unit, how these sensors can be used in a self-driving car technology. Also, along with this kind of sensors and what are their workings, we will also see how the data from two different sensors can be merged together or fused together to get better accuracy of information. Okay, so that is where we will focus on a technique called as multi-sensor fusion. And there generally we will focus on two different kinds of fusion, that is the camera and lidar fusion, as well as lidar and radar fusion. And towards the end of my talk, I will show you some of the data sets that are available in this area, and how we are working in these research fields. Apart from the data that we collect, what are the different data sets that are currently available worldwide, that also we are going to see. Even we will focus on some of the data from Indian scenarios more specifically. And then I have prepared a demo, if time permits, that I will show and then summarize. So this is the whole content that I am going to cover in today's talk. So first thing first, when it comes to self-driving car, what is that, right? So self-driving car, as the name suggests, or even if we go with this term like autonomous vehicles, so you see the first part is autonomous. Autonomous means itself is doing something on its own. Okay, so that is where the name derives as self-driving. See, the car should drive by itself, or the car should drive autonomously without the help of any human operator, right? So nowadays, whatever the cars that we are seeing on the roads is the car driven by the drivers, right? So the driver as a human being, let us we are driving the car. So how do we perceive the environment? First, let's say we have eyes or binocular cameras, I could say, because we have two eyes by which we first visualize the scene, and then from there on we take some decision how we should move such that we will not enter into any critical scenario that would be hazardous for us, right? So that is one of the sensors. Then other sensors could be like we can move our head and see what is going on around us, right? Even we can see the things from the front camera. Apart from that, there are like if someone blows a horn or someone calls you, that also you can hear through your ears. So as a nutshell, we can say that the human being is equipped with the different kinds of biological sensors, and from those biological sensors, whatever the data comes out of it, we take some decision, and based on that decision we need to move the car. That is how a driver driven car is run. Now if you want to replicate the exact same thing in a self driving car, then we need to have some sensors that could do the exact same kind of task that was done by the biological sensor, right? So that is where all these sensors like this camera, lidar, radar, GPS, everything comes into picture, right? So camera, can we can think of like it is a eye sensor which can give you the visual information around you. Okay, so similarly lidar has some working, like lidar can give you direct 3D information that we are going to see. Then every other sensor does some task as compared to the biological sensors, such that the task can be done, right? So it is like all these sensors collect the data, then this data, like as a human being, our brain processes everything. So this data, once it comes, then it has to be processed. So there would be a fully fledged computer system which will do all the processing, and from there on some decision will be taken. Then that decision will be converted to a command, and that command will help the car to run autonomously. So that is the whole set of things that happens behind the scene. Then apart from, when we are thinking about the self-driving car, it is not just one car. There could be a, like in this picture that is shown, you can see I have taken this from one of the websites that I mentioned. So you see, it is not just about one car. There should be multiple cars or multiple vehicles in general. I can say it's multiple vehicles. It could be cars, it could be trucks, it could be even bicycle, not bicycles like in the saying motorcycles, it could be anything. So multiple vehicles would be there on the road, and everybody needs to be autonomous. If you are thinking about a hybrid where some vehicles should be driven by the car itself and some vehicles will be driven by the drivers, then it would create very lots of confusions, right? So when we are thinking about a self-driving car environment, we are thinking about an environment where all the vehicles should be autonomous, right? So in those kind of things, every vehicle would be equipped with this kind of sensors, and also there would be the vehicle to vehicle communication or B2B communication that is going to happen between these vehicles, so that data can be shared between them easily. Okay, even we have filed one patent where we are saying that instead of connecting different kinds of sensors to individual vehicle, how we can leverage the infrastructure where in the infrastructure itself different kinds of sensors should be connected, and from there on the data will be shared to different kinds of vehicles, and from there on a centralized decision can be taken by which the traffic can be managed in an urban scenario. Okay, so these kind of futuristic patents are also filed. Okay, so that is where we are moving. Maybe if we see the current scenario, it might not look like it's a feasible task, but believe me, in some of the developed countries, it is already been implemented. Okay, the self-driving car technology. You must have seen some of the videos where they show say, how the car is moving. Even in India, in case in controlled scenarios, people have come up with demos where they actually show the vehicle running, okay, autonomously, but in controlled scenarios. I will come to that. What do you mean by a controlled scenario and what do you mean by a pre scenario, right? So this is what the self-driving car is in a nutshell. Now, if you think about the market perspective, according to a survey by Global Autonomous Vehicle Market, it is being shown that the global autonomous vehicle market is expected to reach $557 billion by 2026. Okay, we are already there. That means it has grown. This survey was in 2019. Okay, so we are already at a stage. We are currently in 2025. So by 1 year, you will see that in most of the countries, this kind of autonomous vehicles is going to be the reality, and it has a cumulative average growth rate of 39.5%, almost 40%. So that is the way it is growing on, right? So of course the market is currently moving towards autonomous vehicles. Okay, and if you read the research articles, you will see that along with the term autonomous vehicle or self-driving cars, they will use this term called as advanced driver assistance systems, or in general ADAS. Okay, because you see that it's not like today the vehicle is running with the driver, and tomorrow it is going to be like driverless. It is not a 0-1 term like today nothing and tomorrow it is going to be autonomous. So there is a step-by-step procedure, right? From driver aided to driverless. To make it happen, it will go step by step, and we will see that there are actually 6 steps to do that. Slowly the computer system will help the driver, and slowly the driver dependency will go down, and at the end when we reach to that level, we will see that it is the driverless or self-driving car. Okay, so that is why this is also known as advanced driver assistance systems, or in short form or abbreviation ADAS. If we think about the different kinds of market players who are working in this kind of domains, we'll see that every company who are associated with automobiles, you'll see that they are working in some way or the other to make this technology as a reality, right? So if you see the different kinds of companies such as General Motors, Daimler, Ford, Toyota, even Tesla, you must have heard about Tesla, right? Elon Musk. So every company who are associated with the automobiles, you will see that they are involved in this kind of technology. Along with the actually making the vehicle, you will see that there would be other companies which would actually provide the kind of the supplies that are needed for these autonomous vehicles, because you see the kind of supplies, the mechanical supplies that we need for the mechanical cars that we have currently will be little bit different when it becomes autonomous, because there would be different kinds of sensors, there would be like software system, there would be connections and everything. Okay, so for that the kind of supplies that are needed, that also going to be different. Also the technology providers should be there, like in these companies like Wemo, Nvidia, Intel, they work on like providing the actual software actually required to run the system. Then there are service providers who use this car as well as this technology to run it autonomously actually on the car, like this Uber, Lyft and other companies are there. So there are many marketplaces that are there who actually work day and night to make this futuristic technology as realistic. Yeah, so this slide actually I don't know whether it is visible or not, but I will explain one by one. So this slide actually shows why this self-driving car technology or autonomous vehicle technology is known as advanced driver assistance system. Okay, so it goes from level 0 to level 5 autonomy. So level 0 means the driver is completely driving the car. The cars that we are currently seeing on the road, we can say that it is the car that is level 0. Okay, so there is no level of autonomy there. There is no level of autonomy, because you see the you can see in level 0 I have written the driver is fully responsible and permanently carries out all aspects of the driving. Okay, everything is done by the driver, and there is no assistance to the driver from any computer system. Okay, so the cars that we are seeing on the currently on the road, we can say that that is the level 0 autonomy. Now from level 0 autonomy, we will go to a mode called as assisted mode, which has two levels, level 1 as well as level 2. Now, when we are thinking about a self-driving car or in any car system, you will see that there are actually three types of tasks. One is the steering, one is the braking, and one is the throttle or the acceleration. So these three tasks are there in any car system. Now, if we can delegate these three tasks to a computer system which can do on its own, then we can think that we can make this car autonomous, right? So in case of level 1 autonomy, what happens is that the driver can delegate either steering or acceleration or braking to the system. So any of the three tasks will be given to the computer system. Other tasks will be done by the driver itself. So you see, it's like a we can think of like a hybrid way where the driver is also there as well as the computer system is also there. So some of the task is done by the computer system. That is why you see we call it as assistance, right? The assistance is done by the computer system to the driver, right? So the system will perform one of the driving tasks. As I mentioned in level 1 autonomy, the system or the computer system that I am talking about will do one of the driving tasks. Like it either it can do the steering, or either it can do the braking, or it can do the throttle or the acceleration. So any of the three tasks will be done by the computer system. But when it goes to level 2 autonomy, the driver must permanently monitor the system. So all the three tasks can be given. Two, or we can think of like two or multiple tasks can be given to the computer system. But if all the tasks are given to the computer system, the driver must permanently monitor the system. Okay. So that means the software that is there inside is not fully capable of actually taking all the right decisions. That way we can think of like, so the driver, even though the most of the task is done by the computer system, the driver will be fully responsible or permanently monitor the system. Okay, so he will have the steering on his hand, and he will have the brake and acceleration with his what you say, with his capability, right? So he can control this car and on his way, or the way that he wants, right? But at the same time, the system can be given the task to do it. Okay, so we can think of like in level 2 autonomy, although the computer system is doing, but the software is not, software or even the hardware is not that much efficient, such that we can just leave it to the computer system to do. Then comes the automated mode. In automated mode, what happens is that the software is little bit, we can think of like smart, and it is able to do many of the tasks. And in certain situations, the driver can turn attention away from the road, but must always be ready to take full control again. So we can think of like level 3 autonomy is the controlled mode, or in scenarios where we have everything in control. Like let's say if you want to move in a very low traffic scenario where there is a possibility of getting the persons or the cars are very low. So in those kind of scenarios, the car can run very well without any difficulty. Okay, but if it comes a traffic scenario where it is very, the place is very crowded, then the car might not run on its own. Okay, so that is what is the automated mode. So in this situation, again, the driver should permanently monitor, and he can take the attention away if he thinks that okay, in this scenario there are not many vehicles that are running, so the car can run without any difficulty, so he can just turn attention away or take a copy or something like that. But in general, when it in general, if you think about all the scenarios, it will not work. Okay, so that is why this mode is known as automated mode. And in this mode, the situation can autonomous the system can autonomously control the vehicle on defined routes. Okay, in some of the defined routes, let's say in some factory scenario, you want to have a autonomous vehicle which can move some of the goods from some place to the others, transporting. Okay, and in those scenarios, and if you know that the traffic is very less, then in those kind of scenarios it can work without any assistance from the driver itself. Okay, so that is what is the automated mode is. Then comes the autonomous mode. Okay, so in autonomous mode you will find two levels, level 4 and level 5 autonomy. So in level 4 autonomy, what happens is that the driver can transfer the complete control to the system and devote himself to other activities. However, he can take control at any time he wishes. Okay, so here again, the we can think of like the software system as well as the hardware inside the vehicle. It's more smarter, so it can run anywhere. Okay, but at the same time, there would be a driver seat where a driver would be sitting, and he can take the control upon his wish. So it's not like it is mandatory to take the vehicle driven by the driver, but there is upon the driver's wish he can take the control. So it's like a just before making it fully autonomous this stage, right? So you first, let's say you make a fully autonomous car, but you are not actually 100% sure, 90% sure. So in those kind of scenarios, the driver will be permanently monitoring what is going on. If needed, I will take the call. So in 90% of the scenarios, the vehicle can run autonomously without any issues, but at the same time, the driver would be permanently monitoring. Okay, so that is the autonomous mode. And I can safely say that most of the companies, like I showed in previous slides, they are working in the domain of autonomous vehicles. They have reached up to level 3 or level 4, or we can say that 3.5 or something. They have reached to that point. Okay, but what we are actually aspiring for to actually bring the autonomous vehicle on the road is the level 5 autonomy, which is like the complete, or we can say that the complement of whatever we are currently doing. Like currently there is a driver who is driving the car, and we need a system in level 5 autonomy where there would be no driver. There is no concept of driver. Just driver can be, we can think of like the driver's seat can be converted to a passenger seat itself. Okay, without any driver's seat. So everyone would be passengers. Just you enter inside, you just tell that where to go. You can use the some large language model or something like that, so the vehicle can understand your emotions. So you can just tell, I want to go from this place to this place. Even the car can communicate with you, and based on your requirements, the car will move from one GPS location to other GPS location. That's it. So that is the level of autonomy that we aspire. Although you can see by seeing this slide, it might think like very futuristic project, and it will take so much time. But believe me, as a researcher in this field, I have seen where people have reached up to level 4 autonomy. Just that next stage is there. If that is passed, then I can say that we can reach up to level 5 autonomy without any difficulty. Okay, so that is going to be happen in future. Maybe in India, it might take some time. Okay, because of the kind of roads that we have, because of kind of the demography that we have, and the population that we have, it will be very difficult. But it will come for sure. Slowly, slowly, it will come. Okay. Now, if you go to the ADAS software architecture, there are actually three main components in it. One is the sensing, then the computing, then the actuation. Okay, so sensing component is the one where actually the vehicle senses the data like a human being, using the different kinds of biological sensors, collect the data from different sensors, and then the brain processing happens. Similar to that, you can think of like if you think let's say human being, if you are moving in any unknown environment, forget about the car. Let's say you yourself are moving in any unknown environment. The first thing that we do is that we first scan the whole environment through our eyes and by moving our neck or something. Then we create a what do you say create a map of the environment, right? Now based on that map, we shall take some decisions on how to move, right? So similar to that, let's say you go little bit distance, then we again you encounter few new things. Then inside that map, you update that map, and based on that, you take some decision. Same thing happens in case of a self-driving car or any robotic system. First thing first, to sensing. So different kinds of sensors would be connected to the autonomous vehicles, by which it will sense the environment. So in case of autonomous vehicles or self-driving cars, generally this camera, lidar, radar, GPS, IMU. These are the five very basic sensors that are used. Again, I am saying that very basic. Apart from that, there could be other sensors also there. In some cases, these ultrasonic sensors are also being used. Even in a radar, we will see that how short range radar can be used, long range radar can be used. So different kinds of radars can be used. Even lidar, like multiple lidars and multiple cameras can be used. Okay, so very basic is that camera, lidar, radar, GPS, and IMO. All these sensors are being used. Then from those sensors, once the data comes, okay, so you can see once this data comes, then it goes to the actual computing component where all the computation happens, right? So inside this computing component, if you again see, there are three main or you can say sub modules that are there. One is the perception, then decision, then planning. All happens sequentially. Like if you think about perception, we can think of like it is the short form for perceiving the environment, how the vehicle perceives the environment and knows the environment. That is what is perception is, right? So in perception, again, there are three main tasks that we do: localization, detection, and prediction. Okay, so localization is to know where the vehicle is with respect to others in the environment. Like I told, when a human being enters to a new environment, it first finds out where the different things are. Let's say I enter to a room, so I will see where the chairs are, where the table is, where the, let's say there is a bed, where the bed is. So all these things I will keep in mind with, while taking some decision to move, right? So similar to that, when this localization is to know where the vehicle is, where with respect to others in the environment. When I say others means there could be different kinds of landmark. Let's say on a self-driving car, it could be like there could be cars. If you see, cars are dynamic objects. Generally, localization doesn't consider the dynamic objects. Generally, the static objects which can be taken as landmarks, those are considered as we can say like localization task. So that is the task of localization. Then comes the detection part. Detection is knowing the kind of objects that are there in the environment. So it is like basically a object detection task. Again, in object detection we will see 2D object detection using the camera can be done, and 3D object detection can also be done using the lidar. Okay, so again we will see that the 2D object detection as well as the 3D object detection both have problem, so we will go for the fusion where camera and lidar both can be used. Okay, then comes the prediction task. Prediction task is the finding the like what is going to happen next. So that is what is prediction is. So if you know the, let's say, different kinds of vehicles that are there in the environment, then you can know also where, what their trajectory is and where they will be after few timings or time stamps, right? So if you know that, then you can take a accurate decision like how the car should move such that it will not come in the trajectory of other vehicles. Okay, so that is what is the prediction task. And all this localization, detection as well as prediction comes under the perception umbrella. Then comes the decision, where actually I can think of like these AI techniques are usually both in perception as well as decision component. So in decision, what happens is that two things are there. One is the intelligence and the state transformation. So intelligence is the one where actually intelligence is being used to come up with a decision how the vehicle can move from one state to the other state. So here state is like the where the vehicle is at a current timestamp to where it will go in the next timestamp. So that kind of state transformation happens in case of decision. Then comes the planning component. Again, planning component is of two types. One is the mission planning and motion planning. So mission planning is the one, as the name suggests, how you plan the mission for the autonomous vehicle. So it could be like let's say the vehicle wants to move from GPS location 1 to GPS location 2. Okay, so to move from GPS location 1 to GPS location 2, the vehicle will take a what do you say, a decision like what would be the global planner. So it could be something like let's say the passenger wants to move from place GPS location 1 to 2, and he wants to go in shortest distance. Okay, so a shortest distance algorithm will be run, and that would be the global planner, and that path will be followed. It could be something like the customer could say, "Ki, I want to go through a medical shop, okay, where I will buy some medicines." Then the path could change. Okay, so that is the global planner I am talking about. So at the beginning itself, from one location to other location, one planning would be done. But while moving itself, it will encounter different kinds of adversaries, right? It could encounter the cars, it could encounter some other scenarios like let's say some block is there or something. So in that case, again the car has to take some decision to locally plan from moving to from that position and avoiding that problem, and then again going to its original path. So local planning also happens. So mission planning is like a global planner as well as the local planner. Okay, then comes the motion planner, like while moving the vehicle, what kind of different kinds of kinematics parameters should be set, right? It could be something like if the vehicle, there are not many vehicles and the crowd is very less, then you can, the speed can be very high. Even the acceleration can be made higher, right? So in those cases, but when let's say you are encountering a traffic scenario or you encounter a lots of traffic, lots of crowd, then the vehicle speed should be slow, right? So those kind of like kinematic parameters are set in the motion plan. Now once this is done, this mission planner, motion planner, and how to move from one state to the other in the decision component, then a accurate command is made, that instantaneous command is made, which is sent to the actuation component, where actually the whatever the command is generated, that is being executed. Okay, so as a computer science researcher myself, I generally focus on the computing component. So I don't actually come up with the algorithms for actuation. I generally use the already existing algorithms, or generally I work in the simulators where I try to simulate the autonomous vehicle, where just I have to focus on how to come up with the different kinds of algorithms which can help us in the component of perception, decision, and planning. And if we go more details, we will see that most of my work generally focuses on the perception component, where we try to perceive the environment. Okay, and that we are going to see in my future slides. Now, before actually going to see how actually all these techniques can be, or this AI and computer vision techniques can be used in the self-driving car, we'll see why it is much more required, why this AI ML techniques are required nowadays. And you will see that people are using this AI ML interchangeably, and we will see why they are not the same, right? So if you go to the different kinds of surveys, we have seen that AI is contributing to the transform of a global economy. Nothing new. Okay, we must have nowadays everyone knows this, so this is not that something new. And also, it is very faster as in terms of like industrial revolution. Also, if you see the fourth industrial revolution, there are like three different techniques are there: AI, ML, and robotics. Right? Sorry, AI, robotics are there. One of the main AI, IoT, and robotics are there. So AI and robotics are very important components of fourth industrial revolution, which helps the industry to grow. Now, the actual question that comes to, I think, most of your mind is that why now? Why not before? So, if this AI ML technique that we are currently talking, is this something new? So, if you ask me, the plain simple answer is no. This was there from 1950s. If you see the introduction of AI, you will see that it started in the 1950s with the Turing test. Okay, there was a test then by a very famous scientist in computer science, Alan Turing, where he has done the first level of AI testing. Okay, so it started from the 1950s. Many of the algorithms are proposed in the 1950s to 1980s. Even the deep learning algorithms that we currently see, the convolutional neural networks and all, they were proposed in the 1986-87 itself. Even if you see the current current Nobel Prize in Physics that went to Geoffrey Hilton and the other scientists, you will see that actually they got the Nobel Prize because the fundamental principles of neural network that could be used in physics. Okay, and the algorithms for which they got the Nobel Prize, it was actually proposed in the 1980s itself, 1987 or something. So it is not something new. The algorithms that were there, that were actually there before 2000. Even in the year of 1997, this there was a computer system, IBM computer system, which defeated the then chess champion Gary Kasparov by using an AI agent. Okay, so the AI term was always there. The only problem that the people were, or the researchers were facing, is that there were not enough computing power to run those algorithms. Okay, or we can think of like the computers may not were that much fast or that much robust. Okay, so the computers were there. Those who have used the computers before the even 2010, before, you will see that they were not as much faster as they are currently, right? So the nowadays we can't go below 16 GB of RAM, but we have used system which were like 2 GB of RAM. That I am talking about, which I when I did my BTech from 2007 to 11. So people who have done BTech before that, they would know that even I think 512 MB RAM would be sufficient at that time. Okay, so that is what I am talking about. So from 2008 onwards, I can say that the computers were very so the computer technology improved, the kind of chips that we're using in a computer, that also improved, and the computing power came into picture. So the algorithms that were actually there in the 1980s or so, they were actually be realized in a computer system using this kind of computing power. Okay, then the second point is that the availability of much faster processing units, like the graphical processing units, or in short term GPUs. Okay, that actually helped us to process this data in a parallel way much faster. That is the second point. And the third point being is that the availability of the data. Okay, so if you see this AI ML techniques, you will see that in general very large amount of data is required. Okay, so from 2000 onwards, because of the advent of different kinds of sensors, like this camera most specifically, we got so much of data. Now, because of the data, all these techniques that were there, they were actually proposed based on the availability, or the availability of the previous iteration data. And because of the availability of the data, nowadays the algorithm that were proposed, they were actually realized, okay, in 2008 or not. So that is why it started to boom. Then the, I can say like the fourth point being that the advent of the deep learning algorithms, different kinds of deep learning algorithms. Although the CNN or convolutional neural networks, even the RNN algorithms, okay, recurrent neural networks, that were already there. But because they were able to be realized in a computer system, the researchers were able to come up with different variants of it that can be processed on the kind of data that we currently have. Okay, so all these techniques actually helped this AI ML technique to grow. Okay, and from 2012 onwards, I can say that it has like started to boom like exponentially, and now you know where we are in the year of 2025. It is being used everywhere. Okay, so that is how this AI ML technique has grown. And as I told you, data availability means, of course, AI ML will come into picture, because the kind of processing or the kind of algorithms that we need to process those that much amount of data, coming up with a very mathematical kind of algorithm, or hand engineered kind of algorithm, it's very difficult for a human being. So generally this AI ML techniques, how do they work is that they come up with their own learning. Okay, so from there on they try to learn from the data, more specifically the ML algorithm, not the AI algorithms. Okay, so that is why, because of the availability of so much data in a, even in an autonomous vehicle or self-driving car, of course, the AI ML technique is being used in self-driving car. Okay, so self-driving car is not an exception where, of course, AI ML techniques are being used. Okay, so now comes the question. This term, even in the previous slide, you see I have written AI hyphen ML. So even in you see is AI ML new. So you see AI and ML I am using interchangeably. So the basic question is this AI ML something new? Sorry, is this AI ML same, or are they different? So in the plain simple terms, they are different, completely different. So when you think about AI, it is like the bigger umbrella. Okay, or in very simple terms, what is artificial intelligence is that anything and everything that can be done by a human being, if it can be replicated in a computer system, that becomes the artificial intelligence system. Anything, even let's say you are doing in your mind, let's say if I ask you a question, what would be the value of 2 plus 3, you will say that 5. So you have done some kind of processing in your brain, and that answer instantly comes. Even you write a very simple computer system that can add two numbers and give you a correct the output, you can say that it is an artificial intelligence system. So anything and everything that can be done by a human being, if it can be replicated, then we will say that it's an artificial intelligence system. But when it comes to machine learning, it is a subfield of artificial intelligence, or it is a subset of artificial intelligence, how like it is shown in this slide. So here what happens is that, again, the main task, as it is a subset of artificial intelligence, so the main task is to replicate whatever the human being is doing. But in case of machine learning, the basic difference is that the availability of the data should be there. Okay, or previous iteration data should be there, or historical data should be used. That is what is machine learning is. Then comes another field, that is the deep learning, which is again a subfield of machine learning. So of course the data dependency should be there, and also it will replicate the human task, okay, or human brain. Okay, deep learning is we can think of like a software machine learning. But here we will see that the the neural network concept will be used, like in a human being, like our neurons are being connected, like how we collect different data from different sensors through our receptive organs, and from there on through different neurons this data is passed through, and then some decision is taken, like our human brain processes. Similar kind of task will be done in case of deep learning algorithm, like this neural network. If we are able to do it in a computer system, then that becomes the deep learning. Okay, so in this self-driving car technology, you are going to see how most specifically this machine learning and deep learning algorithms will be used, because we have so much of data. Okay, so how we will leverage these techniques, that we are going to see in my next slides. Okay. Now coming to the AI ML applications, it is being used everywhere. So I don't need to mention any specific field in general, because it is used and everywhere, whether it is healthcare, whether it is cybersecurity, accounting and law, military, robotics, prosthetics, everywhere. You name any field, you will see that some way or the other this AI and machine learning techniques are being used. Okay, so the self-driving car technology is not an exception. Okay, so definitely we have so much of data from different kinds of sensors, like this camera, lidar, radar, GPS and IMU. We have so much of data, so that data will be used in some kind of AI and an ML technique to process it faster. So in my future slides we are going to see how actually different kinds of AI and ML techniques, and more specifically we will see that deep learning technique will be used, how different kinds of deep learning techniques are being used in the self-driving car technology. Okay. Now coming to different kinds of the working of different kinds of sensors, you will see that this camera sensors will mostly help us to different kinds of objects in the environment. So you can see the camera sensor, the blue sensor, they actually help us finding the different kinds of view. Okay, and how of different kinds of objects can be found out. Okay, then there is lidar where we find out the 3D information. Then there are radars which by which we can find out the velocity information. Then other sensors are being used. Okay, so we will come to this slide later on. Again, I will explain to that when we will go through different sensors. Now thinking about the kind of data, so it's not about just like having so much sensors. The actual question is, if all these sensors can provide so much of data, then how we will process them. Now if you think about a camera, it gives so much of data like 20 to 40 kb per second. Kb is the kilobyte, right? So that much of data it can give. Even the if you think about lidar, you see it is up to 10 to 70 kb per second. Okay, so much of data comes from different kinds of sensor. It can go up to 4 terabytes of data per day. Now how to process all this data, because all this data is not relevant, so we need to find only the relevant information out of all this data. Okay, so to process this much of data and to take a decision real time is the most important task in case of autonomous vehicle, and that is where the AI/ML comes to rescue, to process this data much faster compared to other kinds of techniques. Okay, so now slowly we'll go. What are these AI techniques? And first task that comes in this technique that comes is the perception. Okay, so perception, as I told you, is the short form for perceiving the environment. Now, if you go to different kinds of research papers in this area, generally you will find this term situational awareness or environmental awareness. Like in that situation, how the car is aware of the different kinds of things that are there. Okay, so that is what is the situational awareness or environmental awareness, or in general we call it perception. Okay, so how the car senses the environment around it, that is what it is. Then it will find out where its location is with respect to others in the environment, that is the localization that we already talked about. And for this task, different kinds of sensors used, like this camera, lidar, radar, GPS, and IMU. And the biggest problem is that huge amount of data comes, and how to process this data much more faster in the perception module. So generally, there are three tasks: what is the sensing, thinking, and acting, as I showed in the ADAS or the Advanced Driver Assistance System architecture. Sensing first senses the data, then in the thinking component, actually this perception comes into picture, where all this AI and computer vision techniques are being used to find the relevant information out of it, and from there on, a command is being generated. Then that command is passed to this actuation component, where actually it helps the running the vehicle. So it goes in a circular way, sensing, thinking, acting throughout the running of the vehicle from in a one scenario. This sensing, thinking, and acting technology goes in a circular way. Now coming to working of different kinds of technology, different kinds of sensors, you will see that camera sensor will generally be used for like 2D object detection. Okay, so we'll come to this term why 2D and all those things in my future slides when I will explain about different kinds of sensors. So in camera, you will see that 2D object detection, or there is a task called as semantic segmentation, traffic light detection, lane following. All these tasks can be done using lidar. We can do 3D object detection, because you see the lidar is one dimensional up. The kind of data that you will go to is actually in 3D. So 3D object detection will be done, and range estimation like finding the depth and all, we can do that. Then using radar, mostly we can do the velocity and range estimation. Okay, so you can see that even lidar can do the range estimation, even radar can do the range estimation, and how both can be leveraged or fused together to give a better accuracy of information we are going to see in multi-sensor fusion. Okay, so here I have just mentioned that like unimodal models, where only one sensor what we can do, but multimodal models or multi-sensor fusion will come later on. Okay, that we are going to see later on. Then comes the GPS technology or the global positioning system technology. It helps to put the autonomous vehicle in the global frame of reference. Okay, where the vehicle is with respect to others in the environment in a global perspective. Then there is a sensor called as inertial measurement unit. The short term is IMU. It helps to provide the acceleration and the gyroscope information. Okay, that we are going to see. And to the end also we will see how camera, lidar, or lidar radar fusion can be done. Now this is how a actually a self-driving car looks from outside. Okay, So you'll see that generally the camera will be placed at the front. Okay, it will cover the frontal part where the vehicle is moving. But in some of the autonomous vehicle, you will see that they will collect multiples of cameras which can cover the whole 360 degree. Even in some cases, they will have one camera which will just focus on the frontal part, and they will have one camera just focus on the rear part. Okay, so that decisions can be taken much more faster with respect to the rear vehicles also. Okay, so camera sensor is connected like that. Then there is a lidar sensor which is generally placed on the top of the vehicle. Always you will see that the lidar sensor, which is a 3D lidar sensor. Again, lidar sensor can be of again two types: 2D lidars and 3D lidars. So 3D lidars generally are placed on the top of the vehicle, because you will see that the lidar sensor is generally a cylindrical sensor which gives you 360-degree data. Okay, the depth information in 360-degree it gives. That is why it is placed on the top, and it collects the whole 360 degrees, right? Then there are radar sensor, which are again two kinds of like short range radars and long range radars, and mostly they are placed on the side of the vehicle, and they generally cover the different kinds of vehicles and give their velocity information. But apart from that, you will also find there is another lidar sensor. You can see it is placed at the bottom, and generally it is a solid state lidar. You will see a term called a solid state lidar, which is generally placed on the bottom of the vehicle to know different kinds of like speed bumps or potholes. Okay, so to get, because the camera and the lidar which are placed on the top of the vehicle, they will generally not help in finding this speed bumps or potholes if there are any. Okay, so generally this sensor that is placed on the bottom of the vehicle, that helps to find out like those kind of information. Okay, but apart from this kind of sensor, other sensors could also be used. Even multiples of these sensors could be used, but at the end you will see that all of this will be connected to a computer system that are there inside this vehicle. Okay, so there actually the decision will be taken. Okay, all the sensors should be connected there, and actually AI, ML, and computer vision algorithms will be run inside that computer system, and their decision will be taken. Okay, and for GPS and IMU, actually it is not required to put in on the outside the vehicle. Okay, we can place it inside, because it just gives you information. It doesn't generally interact with the environment to get the information. Okay, but these sensors generally are placed outside the vehicle so that they can collect information from outside. Okay. Okay. Now coming to the different kinds of tasks that you could do with different kinds of sensors. So here I have just mentioned these cameras, lidars, and radars. But the GPS and IMU, as I told you, they don't generally interact with the kind of objects that are there in the environment. They just give you the information from outside. Something like GPS can be directly from satellite, or IMU is the car data itself. Okay, the initial measurement unit like acceleration and gyroscope, directly the car data. So they don't have to collect information from outside. Okay, so in this slide, I've just mentioned the kind of tasks that we can do using the camera, lidar, and radar. Using the camera, we generally, as you know, camera image, we do the image processing or computer vision. So using that, we can do different kinds of tasks like traffic light detection, lane following, object detection. Again, in using key camera, the biggest problem that we are going to encounter is the depth information would be missing. So in case of camera, you just get the intensity information, and in that intensity map, you can just get the 2D data. Okay, so that's why 3D information would be missing in case of cameras. So the kind of object detection that we are going to do is the 2D object detection. But using LiDAR, actually, we will get the 3D point clouds where we can do the 3D object detection also. Okay, so that's why you will see that this camera and LiDAR data will be fused together to get better object detection. And from detection also, you will see there is a research area called as tracking. Okay, object tracking, how it could be done. Using radars also, we can do object tracking. So all these three information again can be fused together to come up with different kinds of information, like what are the different kinds of objects, what are the types, and the distance to the different kinds of vehicles, and what are their velocities and all. Okay, and using the even we can do the using the camera, we can do the traffic light detection and all, and we are going to see in my next slides how this can be used. Okay, so any doubts till now? I will just sip some water. So if any doubts, you can ask me till now. Okay, then I can go to my future slides.
Yeah, you can post message in chat box and sir can see the
Yes.
messages, then he can clarify your doubts. Actually, sir, I was muted all the mics.
Okay, okay. So it's okay. They can write down on the chat box. Maybe towards the end, I will go through all of them and answer to them.
Yes, at the end I will open. Last 10 minutes I can unmute all the mics.
Okay. Yes, sir.
Okay, okay.
So let me continue then.
Yes, yes, continues. Oh,
Now we will go through all of the sensors one by one and their working. So as I told you, this camera sensors, we can do different kind of tasks like object detection and so the first task that comes or very basic and very important also is the 2D object detection. Okay, so how this 2D object detection work is done is that it first reads the image data from the camera and provides image based object detection. That is very important because in case of camera, as I already told, the depth information you can't get. You can only get the intensity map of the scene. And inside that intensity map, there would not be any depth information. Directly just numerical values should be there. Now, if you do some object detection, like one of the very important algorithms, I think most of you must have known by now is the YOLO algorithm. You only look once algorithm. That is one of the object detection algorithm in you can think like deep learning algorithm for object detection. So there what happens is that when you pass a image through your YOLO algorithm, it will tell where the different kinds of objects are. Now, if you are thinking about a self-driving car environment, the objects could be different kinds of cars or trucks or vans or bicyclists or passengers, different kinds of objects should be there. Now, in case of 2D object detection, it will show where the object is on the 2D image plane. Okay, so there two kinds of tasks could be done. One is the classification task as well as the regression task. So in classification, it will tell what kind of objects are there, and in regression, it will actually tell where the object is on the camera plane. Okay, so both classification and regression task is done in case of 2D object detection. Okay, again for this kind of task generally there are lots of algorithms are there, and most used algorithm, you know, this YOLO algorithm which has reached up to like version 8, and it started in 2017. From 2017 to 2024, every year they are coming up with their own algorithm, which is like the very best algorithm currently for object detection. Okay, and you will see that mostly nowadays the algorithms are based on neural networks or convolutional neural networks, and multiple classes of detection are supported in those cases, as I already mentioned. But here one point I want to specify is that the, let's say, even if you bring this YOLO algorithm and run it in Indian scenarios, you will see that most of the vehicles would not be detected properly, because as you know, I think if you have gone through the concepts of neural networks and deep learning, you know that your model is as good as the data you have. Okay, if you have good amount of data for a particular scenario, then that algorithm will work very well in that kind of scenario. So this YOLO algorithm is mostly trained on with a dataset called as COCO dataset, which is from a foreign scenario. So the kind of vehicles that they have, the structure of those vehicles, and the type of those vehicles, and the type of objects that are there in the foreign scenarios were quite different from that we have in Indian scenario. If you look about, let's say, auto rickshaws or the tempos that we generally tell, those objects are not there in the scenarios where this YOLO dataset, YOLO algorithm is trained. So if you bring that and actually run in our environment, you will see that these auto rickshaws, even to some extent, some of the cars and some of the buses would not be detected properly because the change in shape and all. Okay, so although they are giving very good results on some of the data sets, they don't generally give very good results in Indian data sets more specifically. So if you are thinking about like, if you think like YOLO data set is YOLO algorithm is very best, so there is no scope in doing any work in the 2D of the detection, you are very wrong. Okay, because as I told you, no, your algorithm is as good as the data set is, right? So if we want to work in, if you want to make this technology actually feasible in Indian scenarios, then we can come up with the 2D object detection algorithm, or we can retrain the YOLO algorithm with our data set that we are collecting. Okay, so generally, when we are using this kind of algorithm or YOLO or the SSD, like the single shot detector algorithm or RCNN, those kind of algorithms, we actually what we do, we try to replicate the same algorithm with our data set, and then only we can run it. Okay, so that is the one task that we can do with the 2D object detection, or else these algorithms are very much standard algorithms, and they are readily available even with Python. Just by importing the package, we can directly use this kind of algorithms. Now, coming to the second task is the 2D semantic segmentation. So, as the name suggests, here we actually segment the image. Okay, so the image would be there. On that image we will segment out. So segmentation means each pixel classification is done. Like in the previous case, one bounding box is given one class. Like let's say a car bounding box, we'll say that this bounding box belongs to one car. But in case of semantic segmentation, each pixel will be given one class. So actually you will find the outline of different objects over here rather than a bounding box. Let's say there is a car, you will actually find the outline of the car, and it will show that the pixels belonging to that region of the car belongs to car class. Even there could be other cars, and those cars will be again given the same pixel value. So what will happen over here is that each pixel will be given a different class, and those colors will be different. Okay, so the cars pixels will be given a color, then the road pixels will be given a different color, the sky pixels will be given a different color, or let's say there are buildings, or there are trees, every different objects will be given different color. Okay, so there will be a clear cut outline that you are going to see with the objects. Okay, so again, for this kind of algorithms, neural network based algorithms are used, or the deep learning based algorithms are being used. Okay, so how does that help? Is that it generally helps you to find, let's say if you find the pixels belonging to the road class, then you can find out the free space where the vehicle can move, right? So those kind of tasks can be done. Okay, semantic segmentation has lots of importance in case of autonomous vehicles. Now this is one image from for the YOLO algorithm, where you see one image. I have not taken a I will show in my next slide what happens in case of a driving scenario, but this is in general I have taken from the YOLO paper itself, YOLO research paper itself. So what do they do is that they take an image as input, and they do some processing. Actually, when I say processing means YOLO algorithm, and explaining that YOLO algorithm can take up to like 2 hours just to go through it. So I have not included the YOLO algorithm in today's talk. But what generally happens is that if you give the input image, at the end it will say that what kind of objects are there. Like it will say that this is a car object, this is a bicycle object, this is a dog object, and it will show the bounding box which completely cover that whole object. Like in this case, this bounding box is a rectangular of rectangular window which can cover the, or rectangular region which can cover the whole car. Like in this case, this rectangular region given by pink can cover the whole bicycle, or the green color rectangular box can cover the whole dog. Okay, so this is what is 2D object detection. Now if you go to the actual traffic scenario, like in this case, you can see it is able to show the truck, it is able to show the bicycle or the car. Okay, but what to knowingly I have put this image, because you can see there are different objects, like this car is not detected properly, or this motorcycle that is not detected properly. Even this car, even though it is detected properly, you will see that this bounding box is not correct, right? So the actual what do you say challenge over here is that it's not about just the detection, detecting with good accuracy. Okay, it's not like 50%. If you so when you are in a very critical scenario like this autonomous vehicles, every decision matters. We need to have like at least 99% of correct information, then only, or correct accuracy, then only we can go for autonomous vehicle. So if these objects are not detected properly, then it is of no use, this kind of algorithms. So even though YOLO algorithm is the best known algorithm, I have run it on this image, and this is what I am getting. That means the kind of algorithm that are there, they actually don't work on different kinds of what do you say visual or lighting, or different kinds of lighting information. So like in this case, if these shades are there and it is not able to properly detect this kind of objects. Okay, so research is still there, how we can come up with different kinds of algorithms which can work on different lighting environments. Okay, so that is one of the tasks. Even these camera sensors will not work properly in, let's say, snowy or rainy environments. So how to encounter those kind of cases. Okay, so that is also very important. And this is one algorithm for this is one example for this 2D semantic segmentation, where you see this top image I have taken as input for the 2D semantic segmentation algorithm. There is an algorithm called as segnet. Okay, so that I have used, and you see every object is being given a different color. Like the you see each pixel belonging to the car object is given the red color. The each pixel belonging to the sky class gives given a different color. The buildings are given a different color, the trees are given a different color, the roads are given a different color. Okay, so when I say different color means the pixel belonging to that class are given a different color. Okay, so that is what is 2D semantic segmentation is. Okay, so how does that help? Let's say if you find the pixels belonging to the road class, then you can get the information like where the vehicle should move, where the free space is. So that kind of information can be easily extracted from 2D semantic segmentation. Okay. Now the next task that can be done using a camera sensor is the traffic light detection. Okay, so that in case of a highway scenario, traffic light is also very important because we need to know where the traffic post is and what kind of color is the current traffic scenario. It's like it could be red color where the vehicle has to stop. If it is green color, then the vehicle can go. If it is yellow color, then either it can take a decision like where to, depending on the distance to the traffic post, it can take a decision like how to stop. Okay, or it can slow down and stop. So those kind of decisions needs to be taken. Okay, so this traffic light detection is also a very important task. Again, this the yellow algorithm can be used for traffic light detection along with the normal detection. Okay, like in this image you can see the normal objects are being detected like this car, pedestrians, all these objects. Apart from that, even the traffic light is detected. Okay, so once the traffic light is detected, we need to know what kind of color it is. That is again through different kinds of algorithms to know whether it is yellow color or green color or blue color. We might not require very high-end algorithms to do that because just by color classification we can do know what kind of color it is. So very simple algorithms can be used. Even you see this kind of a check page to know which way it should move, like it is showing that one way only. If you are going to the left hand side, it's just one way. Okay, so those kind of information can also be extracted from the scenes. Then there is another task that is the that can be done using the camera is the lane or flow detection. Like in this case, two white lanes are there, and the task is that the vehicle should move in the middle of that two lanes. Okay, many company scenarios or factory scenarios, you will see that this kind of task can be done very easily. Even we do not require deep learning kind of algorithm to actually do that. Just by detecting those lines and finding the information like where the lines should be and how to keep our vehicle just in the middle of those two lines is the kind of algorithm that we actually need. So here actually one of the algorithm that I can say that we use is the vanishing point algorithm. Okay, so vanishing point, as the name suggests, it is a point where actually the parallel lines meet. Okay, so generally in physical in the real world the parallel lines do not intersect, but if you see in this picture, you see the line that you are able to see, the left hand side line and right hand side line. If you extend it, you'll see that these lines will seem like they are intersect. Okay, at this point they will intersect at some point. Even if you go to a corridor scenario, you will see that not even a camera, if you only visualize, you will see that it looks like they are meeting at infinity. Okay, so the parallel lines intersect at infinity, and that point is known as vanishing point, and that vanishing point information can be used to actually move the vehicle. If the vanishing, you will always see that when the vanishing point lies exactly at the middle of the image, the vehicle would be at the middle of these two lanes. Okay, so that kind of information can be used to actually move the autonomous vehicle without any difficulty. And these kind of algorithms are also very simple algorithms and can be run very efficiently because there is no need of neural networks and deep learning. So so as I told you, in some of the controlled scenarios when there is not much of a traffic, these kind of lane following algorithms can be used very efficiently to actually run the algorithm. Mostly the some of the custom, what do you say, custom self-driving cars or something like that. If those vehicles can be moved in like in some factory scenario where you are transporting some good from one place to the other, then this kind of algorithms can be used, and very low end processing units can be used for that purpose. We do not actually need high end processing unit to process this kind of data. Okay, so this is also a very important task. Okay. The other task that could be done using the camera sensor is the 2D object tracking. Like it is the next level of object detection, I can say. So in case of object tracking, actually along with detection, what will happen that every object will be given a different ID. Okay. So like let's say if I see you for the first time, I will say that I met one person. But if I know your name, I will say that I know this X person or Y person or Z person. So I am giving a ID to you, right? Or whatever the ID that you have, your name would be there. So that is how we recognize people. So similar to that, if the objects that are there in the environment are given different kinds of IDs like ID 1, 2, 3, 4, like that, then that is what is object tracking is. Okay, so generally this algorithms like this filtering algorithm like Kalman filter and everything can be used for that purpose. So these are the different tasks that we can do using the camera, like the 2D object detection, 2D semantic segmentation, then traffic light detection, lane following, then object tracking, and all those things that we can be done using a camera sensor in case of an autonomous vehicle. Now coming to the second sensor that is very important again is the LiDAR sensor or the light detection and ranging. How does that work? Is that so? Generally, you will see that this LiDAR sensor is a cylindrical sensor of some like 5-10 meters, or I can say like almost 10 centimeters height. So there what happens is that this cylindrical sensor, so I have in one image also. So here what happens is that there would be a laser beam which would be continuously rotating in a spiral way from top to bottom by covering, let's say, some 20 degrees. Okay, we can think of like -10 degree to +10 degree if you take the middle vertical line. So it moves from in a spiral way from top to bottom, and it collects the information. Okay, so how does that work? Is that a laser beam is emitted from the laser sensor? It goes, it hits an object in the environment, then comes back. Okay, so wherever it hits, right, so there it creates a point, because you see, you know the speed of light, which is 3 into 10 to the power 5 kilometer per second. So you know the speed of light, and also you know how much time does it take to actually go to that place, hit it, and come back. So using the proper physics, using the speed and the time, we can actually find out the exact distance it is taken. Also we know at what angle the laser beam is emitted, so you know the angle at which the point is created. So what happens is that it this at short pulses that laser beam goes, hits, and comes back, and in rotational what is a spiral way, it just rotates. Okay, so you will get so much points in the environment. So those points or collection of points is known as the point cloud. Okay, so that point cloud is actually taken as an input to the algorithm, computer vision or machine learning or artificial intelligence algorithms to get the information out of it. Okay, so the complexity over here is that you get so much of information. Okay, and actually you will the biggest advantage of it is that you actually get the accurate depth and angle. Okay, at what angle does it hit? So that is the most important information that we get, that we were not getting in case of cameras, because in case of cameras the depth information was not there, but in case of lidars actually the depth information we can get. So this is how a LiDAR image generally looks like. Again, LiDAR is not an image. So that whatever my previous statement that LiDAR image looks like is not actually correct. It's actually like this is a representational image of the LiDAR. Okay, so we have based on the distance that is that we got, based on that this image can be made just for our understanding. But in general, the image, the LiDAR information comes in like exact XYZ coordinates. XYZ, along with that one intensity would be there based on the lidar intensity at which the lidar beam hit to that object. Okay, so you see in this case the biggest advantage, as I told you, directly get the depth information, but the disadvantage is also there, because you get so many points, because you can think of like in the 3D environment you will get. Okay, in case of camera it is just a 2D plane, but in case of 3D it is like multiple planes of 2D. So much of information are there. Then other disadvantage is that you see so much of sparse data. Okay, so much of black points you can see. No point is there. Okay, so much of sparse data, because in case of camera it is like a continuous information, but in case of lidar it is not continuous. You get so much of sparse data. Now the question comes how to process all this sparse data efficiently in real time. Okay, so that is the biggest what do you say, challenge. I would not say disadvantage. Okay, I would say that biggest challenge in autonomous vehicles to process the lidar data. Again, the kind of task that can be done, you can just extend it to whatever we were doing in case of camera to a 3D, because in case of camera we were doing 2D object detection. Now in case of lidar we can do the 3D object detection. So along with the type of object you will get different information, like what are the different bounding box information. So here the bounding box would not be rectangular, rather a box, actually a box that will cover the whole car. And so you will get the width, height, length, as well as what is the coordinate of that vehicle, at what angle it is, what kind of object it is. So 8 information you will get, like type of object, sorry, what kind of object it is, then width, height, length. So 4, then you will get XYZ information where the vehicle is, along with that what angle it is. So 8 information that we are going to get in case of object detection. Again, different kinds of objects like the bus, truck, pedestrian, everything can be detected. But the biggest disadvantage is that it requires heavy processing because so much of data is there. And biggest advantage is that you get uh, accurate 3D information. Okay, so you see, every sensor has some advantages and disadvantages, right? Like as I told, the camera sensor, it's very easy to process, but at the same time, it is difficult to get the 3D information, right? But lidar sensor, although we are getting the 3D information, so but we are not getting the what do you say? We get so much of sparse data and so much of heavy data, so very difficult to process. So every sensor has its own disadvantages and advantages. So as we move on, we will see that it's mostly like always sensor fusion is the best way to go, where some sensor would work on the drawback of the other, so that we can cover almost all scenarios. Okay, so this is the 3D object detection where you actually see the 3D objects that are there in as their bounding boxes. So here the bounding box is in 3D, as you can see. Okay. Also, you will see that the near portion of the vehicle doesn't have any lidar data, because you see the generally the lidar will be placed on the top of the vehicle, so near vicinity will not be covered properly. Okay, so that information will be missing. So for that matter, we use other sensors like this ultrasonic sensors to actually cover the near vicinity of the vehicle. So again, using lidar, we can do the localization. So this side I can skip because localization I explained little bit. There are different kinds of algorithms for that. Like you can say like lidar simultaneous localization and mapping, or the SLAM algorithms that are there, which can be done using the lidar. So in general, localization is nothing but just to like know where the vehicle is with respect to others in the environment. So when I say others, means it is not like the dynamic objects, but there are some landmarks. Like let's say generally what is done in case of localization is that first the vehicle would be run in some environment to get the information, then from there on a map will be created, and that map will be given as an input to your autonomous navigation algorithm. So the vehicle will have some information already available with that before actually running. Okay, so those kind of localization that we actually do in using lidar. There are different algorithms like the lidar slam or loom. Different algorithms are there for this localization. So in the interest of time, I will not go through this 3D localization. Now coming to the radar sensor, it is again very efficient and low cost and small footprint. Okay, very low cost. One thing I missed in case of lidar is that even in camera is that the lidar sensor is very costly. The 3D lidar sensor that I told, even if you go for a low resolution, okay, generally the resolution in case of lidar is known through scan lens, like how many concentric circles can be made, like in the previous case I showed. Okay, so in that I showed that 64 scan lines. So if you see this image, you'll see that in this case 64 concentric circles are there. So 64 concentric circle, currently you can think of like a very high end lidar sensor, and it will cost you around 25 to 30 lakhs. So that is how much costly it is. If you go for like a lowest resolution sensor, which is like 16 scan lens, it can cost you minimum of 8 lakhs. So we are talking about like very high um, rate. Even if you think about cameras, they are very cheap. But when it comes to radar sensor, it is very efficient with low cost. Okay, so the biggest advantage of radar sensor is very low cost, and it generally works on the principle of electromagnetic waves. Like in case of lidar, it works on the laser sensor. Here, it works on the concept of electromagnetic waves, and it is capable to determine the targets at long range with accurate velocity and spatial information. Yeah, so that is another advantage of radar sensor. It can give you direct velocity. Okay, so velocity, if you integrate over time, you will get the distance information also. Okay, and also it's a sensitivity in dark and poor weather conditions also helps to cover the domains where lidar and camera might fail. So lidar and camera might fail in case of dark and poor weather conditions where the radar can work. Okay, so if you look into the different advantages of radar as compared to lidar, is that it can operate in wet weather, low cost and accurate velocity detection it can do. But if you go to different kinds of disadvantages, it has lower resolution than the lidar. Okay, so it is like a trade-off. Like some sensor will give you much more information, but there would be some disadvantages. Again, that disadvantage will be covered by some other sensor, but again that sensor will have some disadvantages which can covered by the previous sensor. So that's why at the end you will see that multi-sensor fusion will definitely come into picture, where all this data can be fused together. Okay, actually going into the before we are already time, so I will be, so this GPS and ECG sensors which actually collect the external information, they are just sensors that are placed inside the vehicle to collect the information about the vehicle. Like this GPS is gives you where the vehicle is with respect to others in the environment, and this IMU generally gives you like what kind of acceleration that the vehicle has and where the heading is and all those information. That also is very important in the perspective of autonomous vehicles. Now the next task is the multi-sensor fusion. As you saw that the single sensor approach is limited by the fact that each sensor has its own weakness in some situations that we already saw. So combining data from multiple sources to increase the accuracy of prediction. Okay, so we will combine different sensors data to actually increase the accuracy. Yeah. Here the biggest problem, or I can say, I will not say problem, but biggest challenge is that different sensors should be connected at different places of the vehicle. Like as I told you, the camera would be placed somewhere, the lidar would be placed somewhere. Now the question is, the coordinate system that we followed by the camera sensor will be different from the lidar sensor or the radar sensor. So how to bring all those data to the same plane of reference, that is the first task. Then the second task is how to move from one sensor plane to the other sensor plane, right? So we need to find the calibration information, just not the intrinsic calibration, but extrinsic calibration between two different kinds of sensors. That is also very important. Okay, so that is the biggest challenge in case of multi-sensor fusion. This image I have taken from the very known dataset known as Kitty dataset, and you will see that along with the placement of different kinds of sensors on the vehicle, which are at different places, you will also see the different in coordinates axis. Like in case of camera, you will always see that x is towards the front, y is down, and z is towards the front. Okay, and in case of lidar, you will see that x is towards the front, y is towards the left, and z is towards the top. Okay, so the kind of coordinate axes that are followed by these systems are also different. Now bringing all those to a same coordinate axis is also a tough task. Okay, so that is also one of the things that we need to see in case of multi-sensor fusion. Okay, so here one of the tasks, as I told you, this camera lidar fusion, it's done. So you can see that even though they are at different positions of the vehicle, they are giving the same data. Okay, so that is one of the fusion algorithms for camera and lidar. There are different optimization algorithms that we actually follow to do that. I have not included in these slides. We can do multi-object tracking using camera and lidar fusion, like where as I told you, in case of 2D tracking, we can do that also in 3D, right? In 3D, how we can do give different kinds of IDs to different kinds of objects. That's why I've written like 3D multi-object tracking. Again, here we can use this Kalman filter based algorithms. Okay. Another fusion that we can do is the lidar and radar fusion, because you can see lidar can give you range information or depth information. Even radar can give you velocity information, which can be integrated over time to actually get the depth information. Now, both the depth information for one point can be used to for different points in the point clouds can be used to actually go for the fusion kind of algorithms. So generally in fusion algorithms, what happens? This is a block diagram. We can say think of like a Kalman filter algorithm, which takes the data from two different sensors, like in this case lidar and radar data. Then it does some measurement, and finally it gives you a measurement which can give you accurate information, which would not be like based on lidar or radar, but rather it will take whichever is best. Okay, so some information from lidar, some information some from radar, and it will give you a very good depth information. Okay, so this is just a fusion algorithm. I will not go into details of this. Okay. Okay, so different kinds of data sets that are there in the different kinds of data sets we can think of, like this Kitty, Nuisance, Wemo. Different data sets are there in this area. Even for Indian scenarios, there is this IDD data set is there. Okay, so challenges, if we see, like everything that I mentioned, like 2D object detection or 3D object detection or tracking, lane following, everything is one challenge that we can think of. Okay. Um, okay, so there is one demo which already time, so I will not cover that. So in this demo, you'll see that we in the using the Kitty dataset, data set, we are able to do the 2D object detection as well as 3D object detection as well as localization can be done. Yeah. Okay. So in so just 1 second, I got it. Okay. So that brings to the end of the lecture. So let me take the call just to.
Yeah, yes, sir, yes, sir. Yes. Yeah, participants, if may you have any questions, you can interact with resource person. I think very soon he will switch on his mic.
Yes, sir. So that brings to end of the presentation, sir. So yeah.
Yeah, yes, sir, yes, sir. Yeah, participants.
Hello, sir.
Yes,
We were talking about multi-sensor integration. So when we have,
multi-sensor fusion.
like,
Yeah.
say, for a biped, yes, sir, like quadruped or biped or any robot, we have, multiple data continuously coming. For example, for dynamic stabilization, for a robot to walk or to see through the lidar, and and also, I mean, for 3D mapping and all, and also this GPS and IMU, DMU for this one. So when it comes to sensor integration, how exactly the sensor integration practically happening, sir? Because we just collect the data and no, like, can you just brief on those lines?
Yeah. So the first task that comes in multi-sensor fusion is the calibration between these two kind of sensors. Okay. So because the kind of placements that would be done on different kinds of robots would be different. So the camera could be somewhere, the other sensors like this lidar in this case will be at different places. So first we need to find out what would be the transformation metrics that are required to actually transfer from one plane to the other. Or in some cases what could happen is that the vehicle will itself follow a different coordinate system. So how to bring the camera data as well as the lidar data to the same plane of reference, that is the first task. Now once we do that, like in one of the images that I saw, 1 second. So like in this image I saw, this camera and lidar data, they are like giving the same information. Let's say this camera and lidar data are not fused. What you will see is that this lidar data which is hitting to this building, it will actually show somewhere over here. Okay, because we have done the fusion part, that is why they are over here. Now once we get to this data, now you know that this camera intensity, let's say there is a x camera intensity which is showing this point on the lidar. Okay, so now both the information you can pass through different kinds of algorithm, let's say some neural network based algorithm, where the data from the camera will be taken as an input, one of the inputs, and the data from the lidar will also be taken as one of the inputs. Then they will be going through different kinds of levels of neural networks to get the information out of it. That is one of the ways that you can follow. Or one of the ways, other ways that if you do not follow any neural network approach, could be something like, let's say you using the lidar data, you generally get sparse information. So the kind of objects that you are going to, the object types and everything are not that much robust as compared to the camera data, because camera data can give you actually the good intensities, right? So the type of objects that you are going to get using a camera image, it's very much robust, right? So that type of object, as well, if you let's say you know that this is, in this case you know that this is a car using your or car is there, right? Okay, no, or some object is there, so you know that this is an object over there. Now actually finding the depth using the lidar becomes very much easier, because you can know that okay, this is the depth of that object if you have done the sensor fusion. Okay, so that is how you need to do. First thing first, I would say the biggest challenge over here is the doing the external calibration to find out the metrics actually that can convert from one plane to the other. Does that answer your question? Hello, sir.
Yes, sir.
Or was it something else that you were asking? I think this is what we generally do in sensor fusion. Hello.
Yeah,
Well,
others, do you have any question?
basically with respect to like, you have around multiple sensors in one body, like in a humanoid perspective when you
Yes, yes.
build. So when in those case, continuous data will be coming in a testing phase of a humanoid or making it,
Mhm.
and giving a feedback loop
Mhm.
for a processor to understand it. Right there, the multiple sensor fusion, whatever you mentioned, plays a major role,
Mhm.
sir, because
Yes,
multiple
yes.
data should be coming from major like maybe from IMU about self-balancing, right? And
Mhm.
all this lidar for and camera and video for these three things also will come. So in Boston Dynamics and other things, robots which are there, like I was just wondering how is that, what is the technology over there? How is this fusion
So,
at a time happens, and is it? It's all about computing,
so
system
it's about,
computing
sir,
also.
first thing first, as I told you, no, sir, calibration, if you can do properly, the same kind of algorithm that we were using, you can use that, but with different inputs now. So that is the task. This is like first thing, calibration, external calibration. Then once you get the fused data, take that fused data to use it in your algorithm. So that is the general state.
What which algorithms you usually do for multi-fusion, sir?
uh, Algorithm, generally it is, these are the optimization algorithm. We generally for self-driving cars, we take a checkerboard, and on that checkerboard we try to find out the let's say there is a black check box is there. So we'll put one point on the checkbox of the black dot on the image plane, and we'll also try to find out the same black dot on the lidar plane. Similarly, I will find like minimum 9 points are required for that. Once we got those 9 points, let's say from 2D intensity to a 3D point, XYZ point. So once we get these 9 points, there are different optimization algorithms which will help us to transform from one plane to the other. So it is like a what you can say, 2D to 3D transformation we are doing from when we are going to camera to lidar, so which is not solvable. But with these 9 points, we can come up with an optimization that can solve it. That is one of the algorithms. The other algorithm is that we can use direct neural networks also to do that. Like let's say you already know, like this KT dataset already does that. There is a camera image and corresponding lidar image, and its calibration metrics also it keeps. So if you know the camera image and the lidar corresponding lidar and the corresponding calibration metrics, transformation metrics, so you can take this camera image and lidar image at the input and the calibration metrics as the output, and you can train on the whole data set. So at the end, when you give a new camera image and the corresponding lidar image, it will give you the corresponding calibration metric. So that is the other way that we generally follow.
Yeah,
Thank
thank
you,
you,
sir.
Doctor. Yeah, please, Ravi Kumar, please. Professor Ravi Kumar, please.
Thank you, Sir. Thank you.
Yeah, thank you, Dr. Ram Prasad Padhy.
So
Hello, sir.
any other questions?
Yeah, I think they don't have any questions. Ram Prasad, sir.
Yes,
Yeah,
yes, sir.
yeah, thank you for accepting our request.
Yeah, thank you, sir.
I'm
Most
very
welcome.
happy you are in
It's
Bhubaneswar,
my
Idle
pleasure to
Einstein.
actually, yeah. Actually, I
Yeah,
came to my hometown, so that's why I,
yeah, it is there, na? That's why you stay.
yes, sir.
Yeah.
Okay.
Okay, thank you, sir. Thank you for
Yeah,
accepting our request. Nice lecture.
yeah.
Okay.
Thank you very much.
Okay, sir. You
Nice
can
to meet
leave, sir. I think another keynote speaker is already joined. We can continue.
you. Okay, yeah, yeah.
Okay, bye
Bye.
bye.